I'm having tech difficulties here, trying to get this thing to cooperate tonight. I'm gonna minimize everything for a minute or two. I'm trying to load November 5th's video across to the page for the lecture segment of this. So hang on a second. It's been one of those days. Things are kind of like not exactly going according to plan. Did I fix it? I hope. I am juggling too many things right at the moment. It's like I had loaded the November 5th video up to YouTube so that they would translate it. But then when I tried to cut and paste it or copy paste it, it had some really strange glitch. So I was trying to have another go at pasting it, and I think it worked this time. So I think I'm only one video behind at this point. I need to download the one from Tuesday, which was what? The 10th of, because Zoom codes them on my end by the date that I did them. And I'm still missing some people. Actually, I'm missing a lot of people. That's kind of odd. There's one more person. I'm wondering if people are having internet connectivity issues because of all the massive amount of rain that has happened today.
I know there's a couple people I've talked to from work today that have had some issues with the internet. So
yeah, I'm not surprised. I think we got like 3 inches, 3.5 inches, something like that, from about 7 or 8 o'clock last night all the way through. And of course, it's still raining at my house. Not super, super hard, but it is still raining.
Yeah, it's been pretty steady. It's supposed to let up tonight.
We all need an arc.
Just about.
Somehow this has just become like super par for the course. In terms of 2020, it's like nothing ever goes really according to plan these days.
When it rains, it pours.
Yeah, my teenage girl is supposed to go to an outdoor event tomorrow with the co-op that we belong to, but I don't know if that's going to happen or not. I got an email earlier that said we're probably not going to declare it happening or not happening until about the middle of tomorrow morning. So I guess I'm going to be kind of watching my email, find out if we're supposed to drive out to Suffolk. It wasn't supposed to happen until 1 o'clock anyway, but thing. How many people have I got? I've got 9 people. That's still not the usual number. I wish I had different kind of Tinker Toys to show you the way the electron cloud pictures look like. I've got pictures embedded in the notes for this chapter, but sometimes having 3-dimensionality helps a little bit, but I guess we're kind of stuck with what we've got. All right, so let me pull up my notes page. All right, so we ended with, did I do that right? Can everybody see the notes page?
Yes.
Hopefully, okay. Okay, somehow or other, I wasn't sure if I hit the right button. We ended with talking about the changes in atomic theory over the time frame, over the timeline, starting with Democritus and sort of ending with the present day quantum theory version. So what we want to talk about some tonight then is what exactly does that weird and fuzzy looking little picture that's shown up there in the corner actually kind of represent? When we start talking about these things that we call orbitals, they have descriptors, things that tell you about where an individual electron is. And we're going to call these quantum numbers. They tell you properties about the orbitals. They tell you things that indicate how many electrons are in that orbital. It also actually indirectly gives you information about shapes. So all of that kind of fits together. This is a big concept that has a lot of sort of different little moving parts to it. The first one of what we're going to call the quantum numbers is referred to as the principal quantum number. And you will see different textbooks will label it with the lowercase n as kind of their symbol. You will also see that they talk about there is an upper limit to the values this can have. It's all whole numbers. You don't start at 0, you actually start at 1. And it tells you which layer the electron is in terms of the relationship to the nucleus. So let me see if I can use the whiteboard and draw some really bad artwork. All right, so let's do this. All right, so we're going to have, okay, that's the nucleus. And then we have the first layer and the second layer and the third layer. So if I go back and I do this, I can call this one layer 1. And then up here, I can call the next layer 2. And I am going outward because 1 is the one that is the closest to the nucleus. So we'll label this one, that we'll label the middle of this N for nucleus, or NUC for nucleus. All right. And then going back to my really crazy drawing here. So you've got 4, you've got 5, you've got 6, and you've got 7. 7 being basically the circle that is the farthest out. So if you're all the way on the outside edge, you are in layer 7. The way the textbooks talk about this is if you are more than 7 layers away from the nucleus, you usually prefer to it as the electron has left the building, okay? The electron is no longer orbiting that nucleus. So I think there's a variation on this idea in a figure in your textbook. I'm not absolutely sure. But I wanted to give you just kind of a vague idea on the fact that we're starting here in the middle and we are counting outward toward the outermost layer there. All right, let me go back to regular note stuff. All right, you will also see these sometimes referred to as shells. I've taught from a number of different textbooks over the years. Sometimes they call them layers, sometimes they call them shells. It actually doesn't make a super big difference what term you are using, but it sort of all applies to the same idea. So once you've decided which layer it's in, then we get to quantum number 2, known as the orbital quantum number. This is another one that you will sometimes see textbooks referred to as the angular momentum number. They're stealing a piece of terminology from physics. Angular momentum is usually used in physics to help describe motion that has a curvature to it. A lot of times, things going around an axis. In this case, you could sort of loosely describe the nucleus as your axis point. Different letter of the alphabet for their symbol. It's not actually a 1, it's supposed to be a lowercase l. What this describes for you is the shape of the orbital. So if the top one, if the principal quantum number is referred to as the shells themselves, you will sometimes see this referred to as subshells, or occasionally they will refer to them as sublevels. Each of them has a letter. SPIDF. Me and my brain tricks of like trying to remember things that have symbols that represent information. S, P, D, F. And they also more or less occur in that order in terms of complexity. So here is a halfway decent picture of the S ones. And by coincidence more than intention, you can loosely associate the word spherical with the fact that they are S orbitals. Now note, we've got one on the left-hand side that's labeled 1s. We've got one on the middle here that's labeled 2s. And we've got one that's labeled 3s. That's a way to sort of describe the layers. So 1s is the layer that is closest to the nucleus. going outward with, in this case, 3s being further from the nucleus than the 1s or the 2s is. Think of it more like layers of an onions. As you look in the onion slice, you've got the bit that's small and close to the center, and then you get bigger and bigger rings as you're going toward the outside of the onion. And that sort of gives you the same kind of idea here. From S, we proceed to P's. Now, P orbitals are often referred to, and I have no idea who came up with this term because I think it's really not a very good descriptor. They refer to them as dumbbell shaped. Now, it's not like any pair of dumbbells that I've ever really seen. I think it looks like a pair of teardrops where the pointy end of the teardrops are in the center where the nucleus is. Now, they are labeled by their axes. So if you look at the first green one here, that says px orbital. So think 3 dimensions. When you're doing algebra, straight algebra, you've got the x-axis is the horizontal axis. We've then got the right-hand one here that's labeled py orbital. So it is an up and down orientation of that pair of teardrops. But since we have to do this in 3 dimensions, we've also got PZ. Remember that a z-axis in upper levels of math as well as physics, the z is kind of like in and out of the plane of the paper. It is your 3rd dimension. If you layered them so that they all sort of overlapped a little, you get this final picture here that looks like a flower. It's got 6 petals, but they did actually helpfully label for you the X, the Y, and the Z. So one thing that is true about all of the p orbitals is that each orbital that has its own individual picture, each little pair of teardrops, has 2 parts to it. Since it's 2 teardrops with the pointy ends inward, you can kind of think of it as loosely like the left-hand side and the right-hand side, or in terms of the PY one, the top part and the bottom part. As we progress from P's to D's, we get more complexity in the possible shapes. Now, if you look at 1, 3, 4, and 5, each of those has 4 teardrops. There are 4, okay, they call them lobes of the d orbital. And these are not actually labeled quite as nicely as the p ones. They're not just X, Y, and Z. These ones, don't worry, you're not going to have to replicate. You're not going to have to draw these. They labeled them in part due to how they're oriented in 3-dimensional space, but also to some degree, how much of the teardrops overlap in a given axis. So if you look at the left one there, we've got the label says dx squared minus y squared. Part of the implication in that is to remind you that that particular version of the orbital doesn't have a z. It's all kind of flat. And then we're skipping the one that has a donut in it for a minute. We're going to come back to the donut one. The third one has DYZ, the idea there being that you have it kind of tilted up on its side such that some of the teardrops are pointing upward or downward, but they're also kind of in line with the y-axis. Then we've got XZ, which is same basic idea, but swiveled about 90 degrees. And then you've got, instead of swiveling it, rotate it so that it's more vertical, and you get the last one's called the XY. So back to the donut. One of the things that comes out of the math. Now remember that all of the quantum theory stuff starts with the idea that an orbital is a three-dimensional probability map. So being that my big kid is taking Calc 2 this semester, one of the things that the calculus or the math classes are using for their calculus classes this year is the Wolfram Alpha website, which if you put functions and calculus limits and things like that in it, it will draw the graph for you. So kind of think about it this way. There's a math equation, a complicated math equation that allows you for each of these orbitals that you're seeing to have a certain solution set. Well, one of the solution sets for the d orbitals has two lobes, but then it has a donut. Now, if you slice the donut in half like a bagel, you would actually end up with 4 areas. Because this is kind of how the d orbitals work. Each of the d orbitals has 4 general areas involved. So do a bagel slice through the donut. You have one part that's pointing upward, one point that's pointing downward that are tear-shaped. That gives you 4 parts. Then we get to the most complicated versions. All right. They're pretty in a really strange kind of twisted way. The F ones have 7 pictures. Now, instead of having 1 donut on a stick, 3 versions of the mathematical solution to the F orbitals have 2 donuts on a stick. One of them is pointing more or less up and down. One of them is pointing more or less in the X directions. And one of them is pointing more or less in the Y directions. If you squint and you look at the little tiny labeling that is underneath that top row there, you'll notice that each one starts with one of the axes cubed as their denoting label. So the first left-hand one is a Z cubed. The middle one of that top row is an X cubed. And the far right one is a Y cubed. But since we're doing this all in terms of probability, then the other thing that's true about F orbitals is all of them have 8 sections. Now, granted, if we're talking about all the balloons tied together, seeing the concept of 8 sections is sort of more visual, because you can kind of look at the lower row there and see, okay, there's sort of 4 balloons poking upward and 4 balloons poking downward. Oh yeah, that makes 8. This goes back to bagel slicing. When you're looking at that top row, you have 1 up, 1 down, but then each of the bagels is also sliced in half, which helps you kind of head in the direction of having 8 segments. like I said, don't worry, you're not gonna have to draw these.
Excuse me,
One thing-
Professor.
Yes.
I apologize. I did come in a little bit late. And are these all different views of the same piece, or are these like 7 different mathematical explanations of the same thing?
Well, okay, think about it. Okay, when you're doing upper level math, functions and limit stuff often has more than one solution, which makes the mathematical equation true.
So these are probability.
Yeah, these
clouds?
are probability maps based upon potential solutions to the
Thank
math.
you.
And granted, we're not even looking at the math because the math is nasty. The math is like vector calculus stuff. Okay. It is nasty stuff. So we're not even looking at the equations that generate these. We are just looking at the solution sets, basically. Did that help?
Yes, ma'am. Thank you so much.
Okay. So one of the things that's also true as we're heading in all of these quantum descriptions is that each sublevel only has the number of pictures available or less. So let me scroll down just a little bit here. So if you have level 1, this is the level that we said is closest to the nucleus. Level 1 only has S's. There are no 1Ps, there are no 1Ds, there are no 1Fs. There's only the round ones. But once you get to level 2, so now you've got a little bit more physical 3-dimensional space, we've got S1s, but we've also got Ps. So you can kind of think of them as overlapping. If you drew a circle, which was your S1, and then you layered over top of it the little 6 petals of your p orbitals, those are all the possibilities for level 2. Level 3 has yet another layer of 3-dimensional space availability. So level 3s can have SPs and Ds. And then by the time you get to level 4, you have SP, D, and F. You will occasionally run across indirect or direct mentions of G's in textbooks, but G's are only even remotely applicable in the excited state. They do not exist in the ground state. So S, P, D, and F are the ones we are going to confine ourselves to. Now, look at the numbers here. We've got 2, 6, 10, 14. If you consider each pictures set that goes with the letters, if you multiply by 2, you get these numbers. So since the S1s were round, and round ones don't care whether they're right side up or upside down or X or Y or Z, if you take one picture times 2, you get 2 electrons. So let me scroll back up here to the P's for a moment. So let's go back and have a look at the P orbitals. So in looking at the P orbitals, we've got PX, PY, PZ. So that's 3 pictures, 3 separate pictures. So scrolling back down here, that means 3 times 2 gives me 6 electrons. 6 seats for my electrons to sit in. The D ones had 5 pictures. So you get 10 electrons. And the F ones, I had 7 little pictures. 3 of the donut on a stick ones and 4 of the ones that have the 8 little balloons. So 7 times 2 gives me 14. Each time you have 2 electrons capable of being inserted in a picture. So in order to reference that idea, we're going to have this thing called the magnetic quantum number. So more alphabet letters here. We've got lowercase m, and it's actually not a sub 1. I know it kind of looks like a 1. It's m sub l. This tells you the orientation. All those weird little cryptic things like z squared minus whatever, those are individual per picture. So for instance, if we start with the sort of the lesser complexity ones, p orbitals have 3 variants. They have px, py, pz. The d one has 5 pictures. The f ones have 7 pictures. So what we're doing here is we're giving you information that tells you what layer, what shape, which part of the shape, and then the last quantum number is referred to as the spin quantum number. More symbology here. We've got m sub s, s for spin. Now, from a purely mathematical point of view, the values that you could assign to the spin quantum number are +1/2 or -1/2. But to give you more of kind of a way to hang this information in your brain, think of it more like clockwise and counterclockwise. Because if you have 2 electrons and they are in the same picture, basically, in order to have them kind of sort of not run into each other, you need to make them have opposite spins.
I'm sorry. Is that the symbol? Is it MS? Is that what that
M
says?
sub S, S for spin. So all of these pieces, all of these 4 quantum numbers funnel into what is known as an electronic configuration. How are the electrons arranged in that atom? All right, so think about it this way, okay? The building that we have lab in, usually when I'm doing this, I'm standing in front of a chalkboard and I can say, the building we're in right now, obviously that doesn't work. The building we have lab in. So it is in Virginia, it is in Norfolk, it is on Granby Street, and it is on one side of Granby Street. So you can kind of think of that as like the layers of location. And so what we can do is each of the electrons that are in an atom, and we usually only deal with one atom at a time in general chem, you can think of the electrons as each one has a spot that it is supposed to occupy in the ground state. So there are some guidelines for this. One of them is called the Pauli exclusion principle. More famous dead guys. Pauli being not one of the original quantum crew, but he was a close follower thereafter. So it says no 2 electrons can have the same 4 quantum numbers. You can't put 2 things in the same space at the same time. It's kind of really what it boils down to. When we package the electrons, there is a pattern to this. Now, I learned it the brute force method and only later discovered that there is actually an alternate way to present the same information. So let me kind of go through it both ways here. We've got what is referred to as the Aufbau. Yeah, nice German word there. Aufbau says, put your electron in the lowest energy orbital or spot that's available. All right. All Aufbau, all electronic configurations start in the same place. Now, in the beginning, the pattern is more obvious than as we proceed. So look at the string of letters and numbers there. All electronic configurations start with 1s. They have to start with electrons being closest to the nucleus. And you fill the slots layer by layer, subshell by subshell, as you have larger and larger elements. So first layer, we said, only has S's. There are no such things as 1Ps, 1Ds, or 1Fs. Now, once you get to the second layer, according to the Aufbau, you have to fill up the S's before you fill up the P's. There are no D's, there are no F's, not in the second layer. Then we hit the third layer. It has S's and P's, and we hit this thing where it kind of looks like it glitched. It actually didn't. Okay, there is a pattern to this. A very strange pattern, but there is a pattern to this. Now remember that in looking at the pictures, the S's were simple. They're just a round ball. The P's, they're not super complicated. They're just teardrops pointing at each other. But by the time we got to the D ones, they're more complicated. Complicated takes energy. So in the pattern of the Aufbau, it is required that you fill the 4s portion of the sequence before you fill the 3D. And then it gets weirder and weirder and weirder in appearance as you progress, because then we've got 4P, 5s, 4D, 5P, 6s, 4F, 5D, 6P, 7s, 5F, 6D, 7P. And it looks like there's no rhyme or reason to that. Okay. And I like I said, when I learned this the first time around, way back in high school, I learned this by the brute force method. You just go for it, just like cram it in your brain. There is actually a pattern to this. Here is the way the patterning works. If you wrote the numbers 1 through 8, 8 is mostly there to make it look pretty because we're not actually using the 8s. And you write from left to right, S, P, D, F. So looking at the bottom segment here, note the arrow goes from bottom right toward top left. And each time as you move up the ranks, you have to drop back down to the bottom right-hand part of that row. So 1s, 2s. Now note, arrow number 3 has both 2p and then 3s on it. Then we get to the fourth arrow. 3p, 4s. Next line, 3d, 4p, 5s. Okay, and okay, they gave you a mnemonic for that. Stupid people drive freaking gas hogs. It's a way, and the G's and H's we don't really use at all. They are only useful at all with excited atoms. For general chem, we are pretty much confining our electron configurations just to the ground state items. But so S, P, D, F. And it gives you the little cursive letter L there. You can use numbers interchangeably with the letters. They do actually equal each other in terms of this concept. The S is a 0, the P is a 1, the D is a 2, in terms of what the L values are referred. I don't spend an awful lot of time focusing on the L equivalents for the letters. If you take higher levels of chemistry, you may come back to that again. I usually just kind of focus on the alphabet, just the way it's presented, 1s, 2s, 2p, 3s, etc. All right, how to use this. When you are given an atom, when a question says, write the electronic configuration for this atom, all of them start at the left-hand end. All of them start with 1s. Now, in terms of what is sometimes referred to as orbital notation, my little arrow that's sitting there on the line, usually you will draw lines or boxes or sometimes circles, textbooks are inconsistent, that represent the orbitals on the outside layer. So hydrogen only has one electron. That's its outside layer because it's only got one. So the electron configuration for hydrogen is 1s1. One electron in an S-shaped orbital, and since the orbital has 2 seats in it, only one of them is occupied, hence the 1s1. And then if I draw my little line, and it doesn't actually truthfully matter whether you draw the up arrows first or the down arrows first, as long as you're consistent. Textbooks differ. I tend to draw the up ones first, but it doesn't really make a difference. So we could say that that one electron that my hydrogen has, let's say it's spinning in the clockwise direction. That's its MS designation, its spin designation. As you progress through the periodic table, you have to use more and more and more of the alphabet. So I'm going to go through about the first 8 to 10 electron configurations, which are the first roughly 10 elements. And then we're going to take a look at a couple of the bigger ones. And that's going to be kind of it for what we're doing tonight. So let's take a look at helium. So periodic table, helium's number 2 on the periodic table because that's the atomic number. We know from way back in chapter 2 that protons and electrons for a neutral atom should match. So helium has 2 electrons. Its electron configuration is almost the same. we have 1s2. So those 2 electrons are in the first layer. They are in a round S-shaped orbital, and both of them are occupied. It has a 2, both seats are occupied, so S2. If you draw the little line, and sometimes problems ask you for orbital notation, sometimes they don't. Sometimes you don't need the arrows at all. In this case, if you drew your 2 arrows, one of them must point upward and one of them must point downward. One is clockwise and the other one is counterclockwise. So now my first layer is full, because remember, there's no P's or D's or F's in the first layer. And once I hit lithium, lithium has 3, but it also means I now have an electron in the second layer. And you always have to fill your Aufbau from left to right, and you are not allowed to skip layers. Sometimes you skip orbitals within the layer, which we'll get to in a moment here, but you can't skip layers. So lithium is 1s2, 2s1. So the first 2 of the 3
But
electrons.
you said 2s1. There's a 2 above the 2s.
Not for lithium.
Oh, sorry. Sorry.
Beryllium, yes, not for
Okay.
lithium.
I'm sorry, I skipped ahead.
So for lithium, the first 2 of the 3 electrons go in the 1s slots. And that third electron is now in the second layer of the ball of electrons. And only one of those is filled in. So again, it kind of resembles my hydrogen in that I have one blank, and the blank has one arrow in it. Then we get to beryllium. So beryllium has one more electron. Now we've got 4. Still, we always have to start on the left-hand side. 1s2, 2s2. But that means on that second layer, which are round because it's an S-shaped one of those 2 electrons is going clockwise and the other one is going counterclockwise. Now we hit some variability in terms of the next couple of atoms here. So we filled up the S part of layer 1, and that was the only option for layer 1. We've filled up a portion of layer 2, only the S part. We still have 6 slots. So I have 3 dashes, and we could label them PX, PY, and PZ. It is traditional. I won't say it's a rule. It's more like a guideline. As you begin to fill the p orbitals, fill them from left to right. So my 5th electron, if I have a boron atom, the first 2 go in the 1s section, the second 2 go in the 2s section. Electron number 5 goes in the px part of the p's, because remember, my p has 6 petals basically. We've got the px one, which is the side to side part, the py part, which is the up and down, and the pz, which is the in and out of the page thing. So now I've begun to fill up the p slots. And now we hit a brand new rule. This is known as Hund's rule. Let me talk about the literal version versus more like the interpretation version. So the literal version says you must fill each orbital of a particular sublevel halfway before you go back and fill it all the way. All right. For those of you who have kids, I will call it the kids in the car seat rule. If you have more than one child and you own a minivan, you will know that it makes your life a lot less complicated if, while you're in the driver's seat and you have two kids, that you put one kid in the middle row of your minivan and you put one kid in the back row of the minivan, so that you don't have to listen to them yelling and screaming at, like, she's touching me, he's looking at me, all those things. Because electrons are all negative. Therefore, they repel each other. Electrons hate each other. They would like to be as far apart as three-dimensional space will allow. So now look at carbon. Now we've got 6 electrons. 1s2, oops, I have a goof. I have a 2s1, it's not supposed to be there. 2s2. 1s2, 2s2, 2p2. But if I look at my slots, okay, I filled up both slots of the 2s. But note the 3 lines which represent px, py, and pz, they're not paired. I have one arrow in the part that I will loosely refer to as the px blank. And then a little bit further to the right, I have an arrow in my py blank. This is how the filling works. You have to, if available, spread out your electrons. Now, sometimes you can't spread them out, because as we look further down the page here, okay, I get to nitrogen. Nitrogen is kind of the extent of spread out ability for my 2p orbital. I have one arrow in the px blank, one in the py blank, and one in the pz blank. And then I'm full. Such that when I get to oxygen, I now am forced to do some pairing. Back to the kids in the car seats. Okay. If you have 3 or more, if you have more than 3 children, okay, if you have 3 children, you could put one in the front seat next to you, providing they're old enough, of course. One in the middle row and one in the back row. Because I have a stepson who is 6 years older than my son. So there was a point in time when he could sit up front, and we could put like the baby seat in the middle row and put the toddler seat in the back row, so that the kids wouldn't fight. If you have 4 kids, on the other hand, you're kind of stuck, because one of the rows is going to have 2 kids in it. So one of the slots in your p orbital is going to have to be paired. And that's kind of what happens once you get to the oxygen segment there. I have 4p. Oh, and I just realized I have glitches in my upscripts here. It's supposed to be 2p2 and 2s2 and 2s2. For some reason, I had 2s1 there. So you've got 2 in the px, but there's still only 1 in the py and 1 in the pz. I still have some empty slots. Later, we will come back to talk about them as being unpaired electrons, which becomes more relevant later. So let me give you two final examples tonight of somewhat bigger atoms. So let's bump up just a little bit. Let's take a look at silicon. Silicon is atomic number 14, so that means I have to find a place to put 14 electrons. 1s2, so that's the first two. 2s2, now I'm up to 4. 2p6, because 6 is the biggest number I am allowed to write above a p, in the same way that 2 is the largest number I'm allowed to write above an s. 3s2, that's number 11 and 12, and 3p2. I didn't draw the orbital notation for this one. If I had, my 3s2 blank would have 2 electrons in it, one up and one down. But I'd have 3 blanks that are px, py, and pz. And 1 electron would go in the px, number 13, and number 14 would go in the py. What if you have lots of electrons? I picked on gold. So gold has 79 electrons. That means you need to use a lot of your Aufbau. You always start in the same spot. 1s2, 2s2, 2p6. So layer 1 and 2 are full. 3s2, 3p6. 3d6 does not come next. Okay, 3d comes after 4s. 4s2. Okay, so that first line there, and I just wrote them in lines because it makes it easier to read and not have them all strung together. That's the first 20 of your 79. The next 10 go in 3d, because d can hold 10. 4p6, 5s2, 4d10, 5p6, 6s2. So I've actually dealt with most of my electrons by that point. I've got 56 that I've already placed. Now that I'm up to a fairly large chunk of my Aufbau, I actually hit the 4Fs. 4F14. Because if you have an F as an orbital, it has 14 seats. There are 7 pictures and every picture has 2 slots. So you can put up to 14 electrons in an F orbital. And Fs don't happen until you reach the number 4. And then my last 9 of my 79 electrons go in my 5d9. Now let me see if I can use my whiteboard and see if I can not make a total mess out of this. Why is it not? Okay, why is it not letting me do the whiteboard? Oh, that wasn't what I wanted. Share screen. Ah, whiteboard. Okay. All right. Clear all drawings. All right. So we will do 1, 2, 3, 4, 5. So this is my 5D, and I can't make it be an upscript, so it's just going to look weird. 5D9. So back to drawing. I'm going to go 1, 2, 3, and yes, I know it looks like my arrows don't have half of their tip on them. It is, I'll call it a habit. For even textbooks sometimes do this. When you are drawing electrons, sometimes your textbook will draw them with only half of an arrow tip. Here's why. Okay, I'm going to go back and put number 6 in, and I'm going to draw it like this. Okay, this is one pointing upward, one pointing downward. Okay, and when you're doing this by hand, not having the tip on both sides of the arrow makes it easier to draw. Okay, so there's a certain sort of usefulness to this. So if I was looking at this 5d9 orbital notation end of my electron configuration, this is how it would look. Of the 5 slots, because D has 5 pictures, 9 out of the 10 slots are filled. Okay, so this is a lot of brain stuff to like kind of all gather up in one set. So over the weekend, go back and look at your textbook and look at the notes again, because trying to wrap your brain around putting all this information into this pattern is often kind of a what moment. When we pick up with this on Tuesday, I will probably give you 1 or 2 more examples. I'll probably try to use the whiteboard thing to do 1 or 2 more examples for that. And then we'll do the last segment of the chapter. This will probably make homework due next Thursday, because we'll probably finish the chapter maybe next Tuesday. So tentatively, homework will be due a week from tonight. So there's a little bit of it that we have already covered that you might want to look at in your homework. The first few problems on the page are stuff we've already covered. So you might want to go ahead and take a stab at that while you have some time over the weekend. But definitely go back and take a look at the pictures in the textbook, because I put some figures in my notes, but I think there's actually more pictures in the textbook. And see if you can kind of get a grip on the patterning for this.
So basically all this doing is when you done the gold,
Mhm.
you can actually go to the highest number for each one of your sets. Like you went to the F, you said, okay, it's 4. So
Yes, fill up all of your packaging until you run out of electrons.
Okay.
So max them out. So like if you were putting eggs in a carton and somebody gave you 20 eggs, okay, so you fill the first carton, that's 12. And there's not quite enough eggs to fill the second carton, but you fill as much of the carton as you can. That's kind of the way the electron thing works.
Okay.
Fill up each package part as you go. Like I said, it's kind of a lot of brain information there. So this is something that people often kind of flounder with a little bit. So some people hate this worse than stoichiometry. It kind of depends upon how your brain sorts the information. All right, I will see you on Tuesday. Actually, some of you I will see on Monday for lab, and otherwise lecture stuff will continue with another couple examples on Aufbau and electronic configuration, and we'll see. We may or may not get through all of the rest of the chapter on Tuesday. I'll kind of wing that a little bit.
All right.
I will see everyone on Tuesday.